Hey, this is Daniil. I need to shut my door. And this is my second integral video on this channel. This is what we're going to be dealing with today. This one is dedicated to my linear algebra teacher, Professor Meyer. And yeah, let's get into it. Okay, so you might already be wondering, what's this outside integral doing? Nothing really. It's just a fancy way of writing a coefficient, because this has no t's in it. So we can basically just pull it out, and the integral of 1 dt with these bounds will just give you this number, which will be multiplied by this integral. So yeah, it is effectively just a constant multiple, but it looks a lot better than just putting a coefficient next to my starting integral, because that's kind of gross. No one likes that. Or maybe I'm wrong. I don't know. So really, this can be expressed as, which also, I don't know if you guys can read that. It's a little small, but this is the number we were dealing with. Very particular, yes, but for good reason. Professor Meyer already knows. But, yeah, so that's just going to stay there. So don't worry about it. And then the real integral that's going to take time to evaluate is this one. Okay, so I would like to point out this integral looks very much like primed for contour integration, but I'm not good at that. I can only do it for like simple semicircle contours that where the arc goes to 0 as r goes to infinity. But yeah, so I can't do more complicated ones, and this seems like a more complicated one because I don't know if we're just using a semicircle or what. So I didn't try that. So I'm going to be using real methods to solve this. To be fair, I don't even know if you can use contour integration for this. I'd assume you can, but anyway. So yeah, real methods only for this one. First thing I'd like to notice is that we're integrating an even function along a symmetric interval. So I'm just going to remove this, turn it to 0, and double the result. This is because we're dealing with an x squared in as the only like x in the problem. So that means when you plug in negative x or x, you still get x squared, which means that the area from negative infinity to 0 is equal to the area from 0 to infinity. So we could just take one of those intervals and double it. So this is the one I'm taking. Okay, now, first thing I'd like to do is I'd like to insert a new variable. We're going to make this, I'm going to call this I, by the way, just so that I don't have to keep writing this nasty coefficient. Okay, so I'm going to stick in a new variable called y right here. You'll see y in a moment. I'm going to evaluate it from y equals 1 to 0. Now, so that means we're going to be evaluating this at y equals 1 and subtracting this evaluated at y equals 0. At y equals 1, we get our target integral I. But at 0, since this is a 2 and not like a 1, which would normally be the case, that means the natural logarithm goes to ln 2 when y equals 0 in this case, instead of just 0. So that means once we subtract this evaluated at y equals 0, we're just going to have ln 2, which can be factored out, times the integral of this, like everything except the logarithm, just 1 over x squared plus 1 quantity squared, which will be a number. And the issue is, that means we're going to get I minus a number. So what I'm going to do is I'm going to find that number, and then I'm going to just add it to this right here. So actually I should say I doesn't equal yet, but it goes to. So anyway, we're going to get I minus a number, so I want to find that number so that I can add another copy of it, which will cancel out the negative that we get from this, and that'll give us just our integral I right back. So let's find it. So we established there's going to be an ln 2 here. So that means we're going to have ln 2 as a coefficient, because when y equals 0, ln 2 is just a constant from 0 to infinity of 1 over x squared plus 1 squared dx. Now, anyone well-versed in integrals will immediately spot the solution method. So I'm not going to waste any time. We're going to do x equals tangent theta, dx equals secant squared theta d theta. Okay, so this transforms to ln 2 times the integral from 0. Oh yeah, so the bounds, when x is 0, theta is 0, and when x is infinity, theta is pi by 2. You can verify that yourself. So we get 1 over, tangent squared plus 1 is secant squared, and we're squaring that, so it's going to be secant squared theta squared. Our differential element is secant squared theta d theta. This cancels out with the squared, which we can, since we have 1 over secant squared, we can rewrite this as just cosine squared theta d theta. Okay, now, you might expect me to use like the power reduction formula for this. No, I'm too cool for that. I will be doing theta goes to pi by 2 minus theta, a phase shift. And I'm also going to use the same variable because I'm a gangster. Okay, so this implies d theta equals negative d theta. Yeah? Okay. So what that has accomplished is the following. We're going to have still ln 2. How do the bounds change? So our first theta is 0, which means our second theta must be pi by 2. And when our first theta is pi by 2, our second theta must be 0. And now the cosine of pi by 2 minus an angle is just sine of that angle, and vice versa, with sine going to cosine. So, and when we square that, we're just going to get sine squared theta, d theta. Oh, and there's a minus coming from a differential, which I will immediately remove after I fix the d in order to switch the bounds. Now, I'm not going to call this integral I sub 1 because it's not really part of the main integral. I'm just going to call it, like, instead of I, j. Why did I do it in blue? I have a system, ladies and gentlemen. Yeah, so this one is going to be j. So we've got 2 copies of j right here. These are each equivalent to each other, so we're going to add them. So 2j equals, the ln 2 is constant. And now since we have the same bounds, we can add the integrand. We can add the integrands together, which will obviously give us cosine squared theta plus sine squared theta. And that's just equal 1. So we're just going to have d theta, and our bounds are still this. This is obviously going to give us pi by 2. And then we divide by 2. Boom. So this is the number we get from this extra little term from y evaluated at 0. And keep in mind, we're subtracting this. So that means, after I erase all this, since we've got an extra term that we're subtracting, which is this, so we're subtracting pi by 4 ln 2, that means our original integral, or well, I, not our original integral, is equal to the same integral we have up there, evaluated at y equals 1 and 0. Plus pi by 4 ln 2. Because we'd have a negative of this from this term, so we have to balance it out with adding that term. And I'm going to call this I sub 1 for the purpose of not having to write this term anymore. Okay, well, not until the end. Anyway, so now what I'm going to do is instead of just evaluating this at y equals 1 and y equals 0, I'm going to differentiate this term. Well, specifically, I'm differentiating the whole term with respect to y, but x squared plus 1 squared is just a constant in the y world. But what that's going to be able to do is after I differentiate it, I can make it an integral with respect to y and make this our bounds. So I sub 1 will be equal to integral from 0 to infinity, well, the double integral from 0 to infinity and 0 to 1. Now, we first have a x squared plus 1 squared already. And then from this natural logarithm term where our y is located, when we differentiate that, we're going to get a yx squared plus 2. And then by the chain rule, since we're differentiating with respect to y, we have to throw in an x squared because that's the coefficient of y in the argument. dy dx. Now, here, one second, it's been a long day. On this interval, any combination of y value and x values, they will not make the function discontinuous. So basically, it's continuous on both these intervals, which also the only numbers that would make this function discontinuous are imaginary ones. So we don't have to worry about that. So since it's continuous on both of these intervals, what we can do is switch the order of integration, which is what I'm going to do. And if you didn't change the order of integration, you could just, work your way backwards. You'd be able to come back to our starting integral. So all of this is legitimate. Like if you switch the bounds again for whatever reason. Yeah, okay, so I had to switch the bounds as well because x is still ranging from 0 to infinity and y is still ranging from 0 to 1. Okay, great. Now, looking at this integral, what do you think is going to happen? What technique screams to be used? I'll let it sink in for a second. We're all in the same boat. Yes, partial fraction. Don't skip this part, especially Professor Meyer. Don't skip this part. Yeah. And hey, it could be worse because x squared is the only variable term we're dealing with. There's no x going around, so we don't have to make a linear term in our decomposition. So I'm going to define a to be over x squared plus 1, b over x squared plus 1 squared, c over yx squared plus 2. Okay, great. Now, in order to get the common denominator, we have to multiply a. So what does a need to get to this denominator? It needs an x squared plus 1 and a yx squared plus 2. B just needs a yx squared plus 2. C needs an x squared plus 1 quantity squared. Okay, great. All of this has to equal x squared. So I'm going to do this, separate it. Okay, so now I'm going to expand this. So for A, let's put an arrow. I'm going to expand the inner terms and then multiply A by them. So the first term is going to be yx to the 4th. So we have a yx to the 4th. And then next we're going to have 2x squared. So it's going to be 2a x squared. Okay, then it's going to be yx squared. So we're going to have a yx squared. And then 2a. For b is simple. It's just going to be by x squared plus 2b, correct? Yes. Plus c. Now, for c, x squared plus 1 squared is x to the 4th plus 2x squared plus 1. So we're going to have c x to the 4th plus 2c x squared plus c. All of this is equal to x squared. And now we can start getting some equations by comparing coefficients. So now, in our numerator, do we have any x to the fourths? No, we don't. So that means we're going to have to take the coefficients of x to the fourth in this expansion and sum them and set them equal to 0. So we've only got two. We've got a, y, and c. So that means a, y plus c must equal 0. Now, for x squared, we've got one copy of x squared in the numerator. So we have to sum the coefficients of x squared, set them equal to 1. So we have a 2a. Okay, there's actually a few terms. So we have 2a, then an ay, then a 2a. No, but what am I saying? Then a by, then a 2c. Yes? Let me make sure. 2a, ay, by, 2c. Right? Okay. So this must all equal 1. And now we have no constants in the numerator, so we have to sum up all the constants and set them equal to 0. So that's just going to be 2a, 2b, and c. So that means 2a plus 2b plus c equals 0. Now, normally we'd just solve these equations in the standard method, but since this is dedicated to a linear algebra teacher, I might as well use an augmented matrix with columns representing A, B, and C. So it's augmented, so we need one of these. Now we're just going to put the coefficients of our coefficients into the matrix, and we're going to solve. So for the first equation, coefficient of A is y. For B, it's 0 because there isn't one. And for C, it's 1. And that entire equation is equal to 0. So next, for the other one, what's the coefficient of A? If we factor out an A from these terms, you're going to get A times 2 plus y. So that means 2 plus y is our coefficient of A. Our coefficient of B is y. Our coefficient of C is 2, and this is all equal to 1. And then for this, it's just going to be 2, 2, 1, 0. Great. Okay, now, for propriety, I'm supposed to write out the row operations that I'm doing, but that takes space and time and effort, and I'm not going to do that. I'm just going to explain it. I'm also not going to write ABC every single time, just at the end, so we're clear on what coefficient we've solved for. So, what's the first thing I want to do? I want to do row 2 minus row 1. That's just going to get rid of the y here and simplify this term a bit. So let's do that. We're not changing the first row, so it's still 0. 2 plus y minus y is 2. Y minus 0 is y. 2 minus 1 is 1. And 1 minus 0 is 1. And then this remains the same. Okay. Next, I want to do row 2. I want to subtract row 2 by row 3. So aka row 2 goes to row 2 minus row 3. So that means we're going to have y01. I'm going to write this a little bit smaller so I don't run into any zeros up there. Okay, 0. And now, we're subtracting this from this. So 2 minus 2 is going to be 0. Y minus 2 is going to be y minus 2. 1 minus 1 is 0. And 1 minus 0 is 1. And then this remains the same. Now, we've already got a row that has no other variables but 1. Meaning, like, there's no terms in the second, or the first and third columns. There's just 1 in the second. So I'm going to just solve for that by dividing both sides by y minus 2, since that's just a constant. We're going to get a 1 here. And a 1 over y minus 2. There. Great. Okay, what else can we do? Okay. All right. I have an idea. First, let's subtract row 3 by 2 over y times row 1, aka row 3 goes to row 3 minus 2 over y row 1. The idea is we multiply y by 2 over y and subtract it from this 2, and that's going to give us 0. So anyway, we're not changing the first row. Still 0. Not changing the second. So this is going to give us 0. 2, because 2 minus 2 times... No. 2 minus y times 2 over y is just 0. This is going to remain 2, because 2 minus 0 is 2. And then 1 minus 1 times 2 over y is 1 minus 2 over y. And then we still have 0, because we subtracted by 0. Okay. Next, I'm gonna subtract row 3 by 2 times row 2 in order to put a 0 here, because we have a 1 here, so I double it, make that 0, aka row 3 goes to row 3 minus 2 row 2. This all stays the same. Okay, so this is going to go to 0. This is still going to stay the same. And now we have to subtract 2 times this. So I'm going to do minus 2 over y minus 2. Okay, now I'm going to divide both sides by 1 minus 2 over y to make this a 1. Let's do some algebra over here. 1 minus 2 over y can be expressed as y minus 2 over y, which will turn this thing to negative 2y over y minus 2 squared. So we can replace this double fraction with just that term. It's been a crazy week, folks. Okay, great. Now, I want to clear out this one. I want to make a 0. So, naturally, I'm just going to subtract row 3. I'm going to make row 1 go to row 1 minus row 3. So we're going to have y, 0, now 0. And then when we subtract this, it's just going to be this term but positive. So we're going to have 2y over y minus 2 squared. 0, 1, 0, and then 1 over y minus 2. We still have 0, 0, 1, minus 2y over y minus 2. Great. And we're almost done. Now, conveniently, we have a y here and a y there, which means we can just cancel them. I'd like to relabel these A, B, and C. So now we have solved for all of our values using linear algebra. Yep, I actually have a piece of scrap paper that I used at school to solve this, so I have to verify my coefficients are correct. Yep, we're good. Okay. Because on my scrap paper, I didn't do it the linear algebra way, I just did it the regular way. So, okay, now I'm going to carefully erase this part, leaving these to remind us what the coefficients are. We have a being equal to 2 over y minus 2 squared, yes. B being equal to 1 over y minus 2. And C being equal to negative 2y over 1, no, y, what'd I do? I missed something. I forgot to carry over a squared. Apologies. Okay, yeah. I thought something was off. Yeah, there's a squared here. Forgot to bring it here. My bad. I did it correctly here. I put it there and I forgot to put it back where it belonged. Anyway, So now let's erase all the matrices. Get back to integrating. Let me check camera. We're still recording. Great. Okay, so now I sub 1, this one. I sub 1 is now equal to the integral from 0 to 1, the integral from 0 to infinity. Before I write the coefficients, let's notice that I can factor out a 1 over y minus 2 for all of them. So, and since that's a constant in the x world, I can just pull it out of the integral, like that. And that'll just simplify our constants a little bit. So for a, we define it as over x squared plus 1, so that's going to be 2 over y minus 2, because we factored out another 1 over y minus 2, x squared plus 1. For b, we defined it as being over this, and remember the 1 over y minus 2 left. And then for that one, we're going to have 2y over y minus 2 over yx squared plus 2. Integration with respect to x, then with respect to y. All right, great. So a couple of these are trivial. The other one needs a little manipulating. So this, if we're integrating with respect to x, this is obviously the familiar arctangent integral, which from these bounds from 0 to infinity will give us pi by 2. So we're going to have pi by 2 times the coefficient already there of 2 over y minus 2. The 2's go away. This one, if you remember at the beginning of the video, I solved the exact same integral, but with ln2 as a coefficient. So I'm not going to go through all that again. You can rewind the video if you want to see the solution to this. It's very quick. Just x equals tangent theta, phase shift, add up 2 copies of I, divide by 2, done. So this was pi by 4. That was the answer we got. This one, I'm just going to call I sub 2, and we'll move it over here. So we have 2y, keeping the negative there. We have this. Okay, so first thing I'm going to do is I'm going to factor out a y, which will go in the denominator and thankfully cancel out this y. And now this is the familiar arctangent thing again. And knowing our rules, if a squared is 2 over y, a must be root 2 over root y. I'm just splitting this up so we can manipulate them later. Okay, great. So that means we're going to have 1 over a, which in this case would be root y over root 2 times the arctangent of x times the same coefficient, so 1 over a, which in this case is root y over root 2, evaluated from 0 to infinity. I'm putting x equals just to clarify, because we have 2 variables. Anyway, at infinity, it's arctangent infinity, which is pi by 2. At 0, it's 0. So this entire arctangent thing can just be replaced by pi by 2. Which means we can cancel out these 2's. And then we can rewrite this as pi root y over root 2 times y minus 2. Great. So that's gone. And now we can just simplify. We've done all the integration. For x, that is. So that means we're still going to have integral from 0 to 1. Now, I'm going to pull out a pi over 4. as a factor because they've all got pi, but I want to specifically pull out pi over 4 because it's going to hopefully make things easier, which, as you'll see, this integral actually has like a really nice collapse at the end, which you'll notice. Anyway, so, and I was surprised about this too, but anyway, so pi over 4. Let's factor. So keep in mind, everything is over y minus 2. You can't forget this one. So I'm going to do this first. So we have a 1, because we had a pi over 4 and I factored out a pi over 4. Next, we had a pi by y minus 2. I factored out a pi over 4, which means I'm going to have to multiply by 4 to that thing. So we're going to have a 4 over y minus 2. Yes? Because pi by 4, we make that pi over y minus 2. Yep. Okay, great. And then the next, we have this. And since I pulled out pi by 4, I have to multiply this by 4, which will make a 2 root 2 appear up here. So we're going to have 2 root 2 root y over no root 2. Just y minus 2 dy. All right. Okay, so my phone ran out of storage as I was doing one of the steps, and I didn't notice because it didn't make a noise. So yeah, I'm re-recording this part. We left off here. I did one more step, but then it got cut out. Anyway, so here, what makes it a simpler problem here, like what makes it a simpler problem is a substitution. So I'm going to write it here. We're going to let root y equal x, meaning y equals x squared, dy equals 2x dx. So this is just going to get rid of any radicals and should make the problem a bit more manageable. Well, visually that is. So, under that transformation, we're going to get, so I'm going to do pi by 2 just because we have a 2 coming from the differential. That's going to cancel out 1. So integral from 0 to 1, as the bounds do not change, the square root of 1 is 1, the square root of 0 is 0. So we have 1. And you know what, actually, before I write that 1, I'm just going to put x over x squared minus 2, because our y's are going to x squareds. And we have an x coming from the differential. So I'm just going to pull that out, just because we're dividing by this already, and we're multiplying by the x from the differential. We're going to have 1 plus 4 over x squared minus 2 minus 2 root 2 x over x squared minus 2 dx. Okay, now let's combine these terms. So I can write, so 1 is equal to x squared minus 2 over x squared minus 2. And when we add that with this, the minus 2 and the 4 will become a plus 2. So I'm going to have an x squared plus 2 here. Let me check my camera again. Okay. And then we can combine these as well. And I'll put the x term first, and then the constant last. So I will have x squared minus 2 root 2 x plus 2 all over x squared minus 2. Now, this is where all the collapsing starts happening, and it's really nice. So this, somehow, I don't know like how the integral just randomly comes to this, but this, despite how weird it looks, can just be factored very simply as x minus root 2 cubed. You could also determine that upon inspection, but it's just nice. And x minus root 2 is coincidentally one of the roots of this, of the x squared minus 2 terms. We have x minus root 2, x plus root 2. So one of these goes away, and then this is going to equal pi by 2. Integral from 0 to 1. Okay, where are we? Okay, so we're going to have an x times an x minus root 2 over x plus root 2. And we can rewrite the other x squared minus 2 as x minus root 2 times x plus root 2. These go away. So I'm just going to rewrite this as x over x plus root 2 squared. Once again, must check phone. Okay, this is with respect to x. Okay, so this one, there's a couple ways you can do it, but the simplest way I believe is integration by parts. So we're going to do, so we have pi by 2. It's going to be all multiplied by, I should make that smaller. It's a large dx, by the way. We have pi by 2. So we differentiate x and we integrate this. So we're going to have x, so our u term, and then minus x plus root 2, because minus 1 over x plus root 2 is the antiderivative of this, evaluated at 0 and 1, which at 0, this will go to 0, so that's fine, and at 1, it's going to be minus 1 over 1 plus root 2. Okay. All right. And then, oops, no closed parentheses, my bad. We have to subtract the integral from 0 to 1, which we can make it a plus because we already have a negative coming from the v term. So it's going to be just 1 over x plus root 2 dx, which you can tell will evaluate to ln 1 plus root 2 minus, at 0 it'll be 1/2. Did I just do a capital L? ln 2. Minus 1/2 ln 2, right? Because this is going to be ln x plus root 2. At 1, it's ln 1 plus root 2. And 0 is just ln root 2, or 1/2 ln 2. Okay, great. So put this in here. Minus 1/2 ln 2. Great. Okay. So this is equal to I sub 1. And we established that I was I sub 1 plus pi by 4 ln 2, which conveniently, again, this problem has like so many pleasant surprises. This pi by 4 ln 2 will cancel with this term, because when you multiply this pi by 2 into this, you get minus pi by 4 ln 2. So in reality, I can just eliminate this and say this equals I, and then our target integral, we wanted, what was it, 2 over ln 1 plus root 2 minus 1 over 1 plus root 2 times I. So then, now it all becomes clear. 2's go away. This term and that term, even though it's written differently, go away. That means that, oh my goodness, finally, final integral is a very poorly drawn pi. You know what? No, that was embarrassing. Pi. There, all that just for pi. I was suggested to do an integral that ends in pi, so here we go. It was a long run, and we finally got there. All right, that's it. See you later.